Great. So, thank you all for coming out to the June 2015 edition of the Scratch Meetup. For today, Colleen Lewis from Harvey Mudd, leader of the CS Teaching Tips project. What?
Okay, so let's start by I'd like to thank CSNYC for hosting this and Cornell Tech for hosting it. So let's start by giving them a round of applause while we wait for my slides to come up. Oh, okay. I'm Colleen. Some of this is going to be me talking, but some of this is going to be you contributing ideas. I hope that I can create a space where you're getting a lot of ideas from other people, learning from each other, and then ultimately we're going to try and take what you say and type into a Google form and put it on the internet for other teachers to see. Okay. By way of introduction, this is kind of what I'm about. I'm about making computer science accessible for all students. The way I do that through both my research and my teaching is trying to understand how students learn computer science and how students feel about learning computer science. Okay? Those are sort of my two areas of research. My two areas of research also I look at, for each one of those, 6th graders-ish and college students, okay, are sort of my areas of expertise. I want to tell you a little bit about myself before we get started. Don't worry, very soon you're going to be standing up and doing a few things. I'm originally from Fresno, California. Have people heard of Fresno? Yeah? Raising capital of the world? What is, okay, no. Okay, and I had a very cool experience. I went to a public school, and I got to learn computer science starting in 2nd grade. I did Logo, which we've had shout out. And if you haven't heard of Logo, I'll show you a little bit of Logo later on today, and we'll talk about that. And I never chose to do computer science, but just sort of fell into it. In college, I went to UC Berkeley and met someone who was going to major in computer science, and she sort of dragged me along, being like, Colleen, it's cool, we can do this. After I graduated in computer science, I worked at Leapfrog. Have people heard of Leapfrog? Yeah? Okay, that's cool. Have people heard of ClickStart, the thing that turns your TV into a computer? That's cool. Let's assume the video camera didn't capture this, so everybody nodded. Okay, whatever. Have you heard of Didge? It's a Leapfrog product. It's like a little thing. Yes. Yeah, thank you. Thank you, Jennifer. And fabulous. So I helped make the included game with the team there. It was fun to work there. Okay. Over the weekends when I was working in industry, every weekend I was trying to volunteer teaching kids computer science. And then I was like, whoa, what if I went to grad school and I studied this? So I went back to Cal to study. I did a master's in computer science and a PhD in education. And then the thing I was doing in my free time for fun of teaching kids became my job, which was rad. Like thinking about that and doing that teaching. So I've been teaching Scratch for a while. I finished my PhD in 2012 and headed to Harvey Mudd College, which is in Southern California. Have people heard of Harvey Mudd? Yeah? Cool. We're a small school, about 800 students. Students major in a science, math, engineering, or computer science. And I've been teaching Scratch that whole time and doing research. Okay, I've got this project, csteachingtips.org. It's sponsored by the National Science Foundation, and I hope from the title you can guess what it is. But we've got 700 tips for computer science teachers, and the way we get these tips is we interview teachers about their teaching practice to try and pull some of these tips out of them. You could be someone that we interview. So after this, you'll likely provide your email address to me in a form today. If you don't want me to email you ever, just don't put it in. And I'll email you to say, hey, would you want to Skype? I can pay people $50 to Skype about their experience teaching computer science. Here's my team from last summer. My team from next summer, Mackenzie's part of it, but most of them start on Monday, so I don't have a good photo of them yet. But the website and a bunch of the great work behind this is this team. And this is a time we went to Google. Can you tell that 2 of the people didn't come with us to Google? Like the poorly done Photoshop? Yeah, okay. The lighting might not be perfect for that, but okay. So here's what we try to put on CS Teaching Tips is not the content knowledge, not like the computer science content knowledge, and not sort of We do some of this, but not mainly the generic information about how to teach stuff in general. You know, but really the intersection of those, thinking about not just how to teach, but how to teach computer science. What's an understanding of the ways to make content accessible, the ways students are going to have difficulty that lies in this space of sort of pedagogical content knowledge. The website also has pedagogical knowledge, partially because one of the users of the website is college computer science teachers who have no training in education. Shh. And so even some of the really basic pedagogical tips that teachers learn and take for granted are helpful for us to promote on the website so that we can try to improve all of computer science teaching. Here's a sample tip. So when I work with students in 6th grade, I work in a room that has computers. And so if I need to make an important announcement, what announcements are not important? I don't know. But if I need to make an important announcement, I stand where I can see all of students' computers. So like if I was making it in this room, I would stand over here where I can see everyone's computers. And then I would say to turn off your monitors. And I would only make the announcement once I had everybody's monitors off. Okay? If I needed them to hear it, and I wanted them to hear it, which is most announcements, I would do that. And the tip on the website also includes information about why this is a helpful practice. And for me, I think it's, this is one of my tips. I think it's really important to value students' problem-solving time. And to respect that, I say, hey, folks, sorry, I've got an announcement. I'm going to have to cut you off in 20 seconds. Okay? And then I'll wait so that they can finish up what they're doing, and then I'll count them down and have their monitors off. Okay? So that's an example tip. What we're going to do today is the goal is to have great conversations, and we're also going to write tips about Scratch. Many of you haven't maybe even seen Scratch, and that's fine. I think that's going to be, you can think of yourself as a consumer for these tips. And so it'll be important to have you in these conversations to say, wait, we need more information. Let's dig a little deeper. You'll write these in groups. We'll structure all this. It'll be, once we get to this portion, you'll be totally fine. And I just want to mention, we'll format them so you don't have to worry about that sort of piece. Typos are fine, etc. OK, so now can I have everybody stand up? We're going to be very careful of the microphone and come and stand in the middle. OK. That's awesome. Okay, have you done one of these things where I ask you a question and I say, have you ever taught Scratch? On that far end is nope, and on this far end is for years and years and years. Yeah? Okay, do that. So that's the left, that's nope. This is for years and years and years. Okay. Now that we're clustered in groups where we have different sets of experiences, I want you to talk in your group. I'm going to give you the instructions, and I'm going to give you multiple instructions before I want you to start talking again. Okay? You're going to be talking about why did you get started teaching Scratch? Or all the way over here, why did you want to get started teaching Scratch? Okay? What we're going to do at the end is after you've gotten to know people in your smaller clusters, we're going to have each of the groups share out some of the reasons, and then I'll write these on Post-it notes and post them over there, and these will be the seeds of tips that we'll put online. Okay? That frame, why is this important? Why is this good for kids? What are we trying to accomplish? Etc. You might even break into like 2 groups, some of the big ones. Okay, start talking about this, please. Go.
That's a whole lot of
so I know Scratch, but I've only taught it to my 2 sons. So.
Oh, actually, that would be a great thing. Okay.
Simplified as they are. And I've seen that within like the Scratch lunches that I've been doing with my 6th graders. So for me, I just see.
Okay, can we raise your hand if you want more time? Raise thumbs down if you don't want more time. Okay, I'm gonna cut you off. We're gonna do 2 more of these before you sit back down again. Can I hear from the Scratch experienced folks, what was a reason that got you involved in teaching Scratch and something that you might say, oh, you should do it because?
blocks programming is the way to go.
Yeah.
Woot woot.
And Scratch is the big kid on the block, so to speak.
And it's unintended.
And it's free.
And it's free. And it's free. Hallelujah.
Love it. Love it.
And now it's web-based.
Can we hear one from the group, from the center group?
Sort of how shareable it is and how easy it is for people to take other people's projects and remake them.
Love it.
Instant feedback.
Instant feedback. Okay. Let's hear from the center or this very large group.
That we said. I mean,
Yeah.
problem solving. It was used for that.
Yeah. So
Of that narrative, tell a story. That it
Awesome.
Could be interdisciplinary. Could you say social studies?
Okay, I've got another one. Did you know some computer science before learning Scratch? That direction is yes, this direction is no. And so this is more like, maybe you don't know Scratch. So have you?
Yeses. Oh, we have to go all the way down.
Yes. So yes, do you know some computer science? Rate yourself from like yes, lots and lots and lots to very, very little. Yes is over there. Okay, we're going to be discussing what helped you prepare to teach Scratch. Like what were things that you did for, you know, someone who knows computer science or someone who doesn't know computer science to help get ramped up on how to teach that to kids. And then within your group, customize as appropriate.
That is the danger. A good way to go at totally opposite is only
Say that again.
Design specific lessons and problems. Because the problem with that teaching Scratch is not Scratch. The problem is
They're going to do it, and then
because, well, that's
So you invent
then
things
they have to switch computers.
to teach.
The card stays
Right.
up for 10 years.
I'm going to add that to a different column, but that tip will be up
Makes
there.
life so much easier.
and then also like what that, how that's different from like teaching computer science. You know, people who have.
So I have my two boys working together.
Good start, right? Your turn.
Okay. Yes, because no, I haven't really taught Scratch, so I'm a school librarian. But I guess so. The computer lab is in our the library media center, and we don't have a separate computer teacher, so it's kind of been my job to kind of take over, not only doing library skills, but then computer stuff I've been working on more with the older kids. So basically, just from reading different teachers' blogs and things, I've seen other librarians or
Which is so when I taught computer skills, they know that they're supposed to learn it.
Right.
It's kind of part of their job description. Right.
But it's learning based on what you already know.
One more minute. One more minute. One more minute.
Right.
So if you were teaching someone then with a Photoshop background, would you try to connect those, or?
I would do a tutorial that would, basically you just have to force them because they won't do it on their own. They'll have a lot of resistance. You just need to, I definitely think that's a different kind of personality. And
I just always find that musical educators. The resistance to learning new stuff has been mind-boggling.
I have not prepared to teach Scratch, but in learning new languages or thinking about how to teach stuff, the first thing I would do is just get my hands dirty with it and come up with some sort of challenge that I'm here's definitely what I want to do, and then research how do I do this.
I don't dispute that. It's more just if we're disagreeing, it might just be about vocabulary as opposed to actual.
No, it's
I'm a lifelong learner. This is what it is.
So forward 100 line without first class. So the idea is to create some items where
Okay, 15 seconds, and then we're going to share out from groups.
Scratch in our freshman class.
Okay. Okay, I'm going to count you down from 10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, can I have a group share out? What were some ideas you had about resources that were helpful for you in teaching Scratch or getting ready to teach Scratch? Michael. Okay. Anyone want to jump in with what, a resource or a strategy they found helpful? Yeah, Sean.
There was sort of a conversation, there was a theme around, if you have a lot of experience, how it connects to other languages or other paradigms, and sort of taking the time to say what does Scratch do well, what is not there, and why, right, from a pedagogy perspective. If something was left out, is it sort of easy to incorporate in, or is it like, no, this really wasn't designed to handle this concept particularly well, but for some reason.
Awesome. Your group want to share one?
I self-taught the course I was going to teach, so I had this pre-existing tool in CS first.
Yeah.
Then I also just made things that were fun for me.
Uh-huh. That's awesome.
Yeah,
I've got those 2 tips already up there. That's perfect. Yeah. Other ones maybe from this group?
Cards were...
Oh, the Scratch cards.
Yes, Scratch cards.
Yeah. So I put that one up there as well, and then when we get to the point where we're flushing these out on tips, we're going to have people take Post-it notes and be like, oh, I'll write this one into a Google form. And in doing that, I've also put some questions on it of like, well, how did you use the Scratch cards? Do you know what I mean? Did you use them with your kids? Did you just use them as an individual, etc.?
And we had paired programming too.
Yeah. Oh, with another teacher.
No, adult kid.
Adult kid. I like it. Okay. Awesome. That's great. I'll get that one. Can we hear one from this group of something that was helpful in getting prepped to teach?
I basically,
Yeah.
I attended a workshop last week, basically, that was my first exposure, and just from reading other blogs that other educators have written, that's where I kind of got the idea to, try and do this in my school.
That's awesome. Yeah. Any other ones we should definitely capture before we move on? I've got the blog one.
Make all the student accounts first.
Oh, I like this.
Let's get real.
Okay. All right. Our next question is, what do you teach? Everything? Only computer science? Okay. And then I'll have another discussion question for you. So, back of the room is you teach everything? Exactly. Okay.
Exactly.
So the question for this group, I'm sorry, I'm going to cut you off. The question for this group is, how do you connect Scratch to other CS learning your students might do? Okay, so how do you connect Scratch to other CS learning your students might do? Okay. Your question is, how do you computer science that way? How do you connect Scratch to other learning that your students do outside of a computer science classroom? What if we split your group in half? Then you get more people talking. Let's take the 4 of you and go that way.
So we're talking about getting the A into STEM.
Oh, yeah.
Yes.
And how do you do that?
How you do that?
Yeah.
You have to emphasize creativity. I mean, it's just like the bulk of it,
And
21st century skill to foresee.
Does that end up being visual creativity?
It's all of it. It's all of it. You have to think outside the box. I mean, it's all of it. Visual, music. I mean, music and STEM go together. You have physics. I mean, how you make instruments. I mean, there's a technical part of it, but there's also the creativity where it's going to,
Oh yeah, and music composition involves a ton of math and pattern recognition
and all that good stuff.
I love it.
First graders,
I think that Scratch will be this kind of like reward in a way. It'll be like this play area where after they learn a concept on Treehouse, they can then, I'll be like, show me on Scratch.
Gotcha.
So it's kind of reversing. Because that's in my life, Scratch is like my fun relaxation play.
Gotcha. One of the other ones that Stephen brought up was like strategic pain points in Scratch to motivate concepts that are better
Oh,
articulated
I
in
love
other
it.
languages.
And we'll come up with specific examples. That's great. Okay, 1 minute, 1 minute, 1 minute. 20 seconds.
High school also.
Okay, can I hear something from your group?
Stephen was articulating using Scratch. So strategic pain points in Scratch that the language doesn't support certain concepts well as motivation for teaching concepts in other languages, other programming environments, etc.
I love it. I love it. I've got that one on a Post-it.
Raise your hand if you're familiar with Project Euler. This side is familiar with Project Euler. I'm looking at you.
Great idea.
Coming up with these real challenging problems and saying just write a Scratch program to solve it and try to get to the heart of math problems, or like math concepts through these simple probability and statistics is my go-to example. I can never remember the difference between permutations and combinations, but I can work with programs and like get kind of a better feel for when I should use one or the other.
Love it. Science?
Yeah. About like one of the cool things about computer science or like any like programming environment is just like this extremely tidy lab where everything is totally deterministic. And so if you can like kind of apply the like scientific method to something, you can say like, I think if I type X, I'm gonna get Y, like, but I got Z, so what happened? And I can go through and I can go like one step at a time in a way that like the real world is just not that tidy. And so it's kind of like a nice like theory of science test ground.
Love it. And I'm putting on these Post-it notes. When you later grab these to volunteer to write a tip for them, example Scratch projects are going to be great, even if you just throw something together and share it, or really detailed descriptions of like what might be an assignment you give to your students. Yeah, can we hear from this group?
That's interesting is we all seem to talk about the hands-on and sort of, you can say physical computing. I mean, so that's kind of a nice idea that the way that Scratch is, you're not teaching Scratch in and of itself, but Scratch is a way to sort of one interface and somewhat easy one to connect to all the other hands-on activities. So that's kind of what I think that we kind of like that. Yeah, like whether it was robots, whether it was a makey, whether it was weaving, whatever, those things are there. There's a range of things that we can use.
Oh my gosh, you guys are awesome. Give yourselves a round of applause and have a seat. So in 2008, I started teaching Scratch to middle school students who were underrepresented in computer science. And I was new to Scratch. And so I just the night before class made a bunch of worksheets. And in many ways, it was a disaster, but a quite pleasant disaster. It was a really small class, so there was limited pain for the students. In summer 2009, I taught a much longer class, a 36-hour class for students entering the 6th grade, and really started fleshing out a lot more detailed curriculum. Again, all the night before kind of development. I had all this stuff planned out for the 36 hours, which was over 12 days. And then in the first 4 days, they finished everything that I had planned for the first 10 days. And I was like, cool. So now I'll spend every night making new lesson plans. Awesome. Okay. Then in the fall, that sort of spring before that, and starting in the fall of 2009, we started at UC Berkeley, where I was going to grad school, developing this course called The Beauty and Joy of Computing. Such a cute name. Also called BJC. Have people heard of BJC? Okay, yeah, so we started developing that pilot. And actually what we did is we took my 36 hours of Scratch curriculum and we spun it into age appropriate for college students. So that tells you two things. One, the 36 hours I was doing with my kids in Scratch was actually really pretty meaty stuff. I was focused mainly on how to take computer science concepts and integrate them into that curriculum. there are lots of different goals that people have in doing Scratch. Coming from my perspective as a computer scientist and education researcher, I was really interested in, can we get kids to reason about some of these complex ideas? BJC has continued. I've continued to do more of the curriculum development with them. I have not continued to do more of the curriculum development with them over the last few years, and they've really been expanding, and they're expanding to New York. Good things there. I've continued teaching Scratch every summer, ... One summer, I had the opportunity to have 3 undergraduate students sit in my class and take field notes. So what they did is we picked out focal students, and we were interested in those focal students' trajectories in this 36-hour camp, summer camp. And so they just sat behind them, you know, like not interacting with the kids, taking notes. And we found is our most like dedicated, attentive students didn't pay attention when I lectured at all, even a little bit. And I had 3 hours with them each day, and it was self-paced during the day. So you work with either a partner or a buddy, and you work through the curriculum. And so that meant that any new ideas that I needed to teach them, I had to teach them at the beginning of class. So I did about a half an hour of lecture with 6th graders. And maybe you're like, Colleen, that was just obviously a bad idea. I'm open to that. It is not my worst teaching mistake, okay? But what that got me to do, and looking through those field notes got me to do, is the next summer in teaching the course, I made a series of 1 to 4 minute videos, 70 of those. And then what I could do is you watch a video, a 1-minute video introducing a problem, and then the student does the problem, and then maybe a 2-minute video explaining the answer to that problem and the big idea that I wanted them to see. Okay, so I got to do more of this just-in-time teaching by, in my class, having students watch videos I had made. Does that make sense? Okay, I've got those videos all online, and then Harvey Mudd was like, oh, this like massive open online course thing. Have people heard of those MOOCs? Yeah? They're like, oh, Harvey Mudd has fabulous teachers. We really should be highlighting that. And so they got money to make some MOOCs. And then I was like, oh, guys, I have a bunch of videos. I like kind of already have a MOOC. And so then they threw me in there with the rest of them, and Harvey Mudd paid essentially to turn my curriculum and my 70 videos into a MOOC on edX. If people have heard of edX, it's just a free platform. So you can, my class is open. You're welcome to use it. I've got slides on the next thing. So I've got more than 70 videos, more than 30 hours of curriculum. It was designed for academically advanced middle school students. It has an emphasis on iteration, which we're going to talk about in a second. And I'm not, I showed you on the first slide, my whole goal is to make computer science accessible. And so if you're interested in using any of these resources, you can use them without attribution. Do you know what I mean? Like take them, use them in your classrooms. I don't need you to waste page real estate by being like, oh, Colleen had this activity, okay? So I hope that some of them are useful to you, and if some of them are particularly not useful to you, that would be super helpful feedback for me. Do you know what I mean? Like if you're like, oh, Colleen, thumbs down. I also have a Facebook group for teachers who signed up on my edX course and expressed interest in using this course to teach computer science. So if you're interested in that, I can send you information about that. Okay. Okay. My course is about iteration, and I want to talk through just some of the stuff I think is really interesting to teach with in Scratch, and how it lets you have many examples of a single concept. Okay. If at any point for non-scratchers, if the content is inaccessible, like you're like, Colleen, I don't get it, I'm confused, I'm happy to slow down. Here I have a script. It's just a sequence of commands that's going to have the character say the numbers 0 through 9. Okay? It does those in order. I can also turn that into a loop. So here I say set the variable my number to 0, And then I'm going to repeat this thing 10 times. So this stuff inside will happen 10 times. And I say my number. So here I'm using this variable my number that I first set to 0. And then I change my number by 1. And so this can do the same thing sort of more compactly or more abstractly. Okay, so it starts at 0. I say the number, I change it by 1. I say the number, I change it by 1. And change it by 1 just means add 1. Okay? Let's do a check-in. We feel good, really great about this, not so great about this. Okay. Yeah.
Are you giving this to us in any particular order? The concepts?
No, that's a reasonable question. I am giving this to you as a peer. Hey, look at how I do multiple versions of iteration in Scratch and how I try and connect those across, because I think that's an important idea in computer science. Does that answer your question? Later on, we're going to do another one of those breakout groups, answer some more questions, and then after that, I'll share some of my teaching tips. And then we'll come and we'll write teaching tips together based upon those post-its. Yeah? Okay. So what I see here for iteration is the central pattern is we set a variable, we have a repeat. Inside the repeat, we're going to use that variable. Here we set it, and then we change that variable. Okay? And this is the same pattern that I make explicit to my students. Oh, this is the iteration pattern. We set, we repeat, we use, we change. Okay? I've got another version of this. We're going to look at 4 examples of that pattern, and there's many more that you can do in Scratch with, I think, cool results. So here I actually set this one, I set my number to 10. I repeat it 11 times. I say the number, and then I subtract 1. Okay, so this one's counting down. Okay? Check this one out. Here I set the variable my note, and I've got a repeat and a change. But instead of saying my note, now I'm going to use the plain note block. And I put the variable in there so that it plays that number note. In Scratch, all of the notes are represented as numbers, so 60 is middle C. Okay? So this is going to play, like, I have no ability to, like, make noises that sound like notes with my mouth. And then up each of the notes. Yeah, something like that. Yeah? Yeah, it's chromatic. It doesn't respect chords. Thumbs up, I feel good about what this one does. Yeah? Okay, and this one, it's not hard for, hopefully, us or for students to see how this implements the pattern. Okay, we set, we repeat, we use, we change. Okay? Let me come to 2 more out there examples. So this one, I set the tempo to 60 beats per minute. I'm going to repeat 20 times. I play a drum, which implicitly uses the tempo that I have, this implicit variable tempo, and then I change the tempo. So this one starts out like this. Yeah? I think this is cool, that the code is so similar, right? It maps directly to it, but the output is so different, okay? Another thing that I think is really cool is in Scratch, there are all of these explicit variables kids have to make and then work with. They set them, they change them, etc. But even before you have kids working with explicit variables, they're used to working with all these implicit variables like position and turn angle and tempo and instrument and volume and pen color and pen size and. And so there's all of these built-in variables in Scratch, and you can use any of them for an iteration pattern and produce sort of like interesting-ish results. In particular, I think iteration is interesting because it's really hard for kids. This idea, this is such an abstract thing where I'm going to use a variable and that variable is going to change within the loop, I think is really mind-bending for kids. And something I see, a lot of kids will start, this is also a tip on the website, a lot of kids will start and I'll be like, oh, play the notes between 60 and 70. and they will make a script like that first one that explicitly copy and paste the block and make it for 60 to 70. And once they get that working, I can transition them to think about, like, can we use your code that I've got? And you can see concretely, your code works. Can I transition that to using this iteration pattern? So having them have many examples where they take this concrete code and transition it to this iteration pattern, I think can help them rock this abstraction. Okay? So I think more examples are just better. Okay, here I've got one more, which is a little stranger too. So I set the pen size to 5, and then my use it is this pen down, pen up, move 10 steps. So what I do is Scratch has got a pen. I set the pen size to just a little pen. I do pen down, pen up, I move 30 steps. I make the pen a little bigger. Pen down, pen up, I move 30 steps. I make the pen a little bigger. Pen down, pen up, I move 30 steps. And I've got this same pattern of iteration. I think it's really cool. I thought about asking you if you also think it's really cool, but I think I'll be sad if you're like, it's not that cool. So we're just going to move on. But so I think there's a bunch of different examples you can use where you use implicit or explicit variables. And you can make them much more complicated. So one of the examples I do is having students draw a rainbow, which uses the same pattern of iteration. Yeah.
Okay, do you use the word implicit and explicit with? 'Cause, like,
I don't use
with
implicit and explicit.
What do you use with sixth graders? Right? Like,
Yeah, I think.
like those two words do not.
So implicit and explicit, I use variables and for explicit and built-in variables.
Okay, that's
Yeah,
fine.
that's fair.
I just wanted to know.
That's fair. That's an appropriate transition.
Would you ever,
Steven.
in teaching this, use any kind of physical piece of paper or something that has an ability to change and gets passed from situation to situation? In other words, making it a physical analog of the concept of a variable. Did that just segue into your next?
No, no, not at all, but I'm going to write it down.
I mean, something that, you don't want to keep a piece of paper where you keep scratching out the number, but if there were some kind of thing that you turned, almost like those little spelling wheels or those number wheels.
Yeah.
Each time you pass it to another person, add 1 to it, pass it, do something, add 1. But just a physical gizmo of some kind, something very simple.
So one of my examples of iteration, one of my examples of iteration is a squiral, which is a square spiral. And so I take a step that's 10 and I turn, and then I take a step that's 20 and I turn, then I take a step that's 30 and I turn. I take a step that's 40. Can you picture what this is drawing? And I turn. And so that is one example where I use a physical manifestation, but a lot of times when I demo that for kids, I do keep a box that I label as my variable on the board, and we keep updating that number so that as the cat, I know how much I should be moving. But that could be another tip, is thinking about how do we bring this iteration into other physical forms. Okay, I have one more of the I think this is cool thing. So here's another example of how I try and give students.
Can you go back in the last?
Yeah. And I can post these slides online. Oh, that's great.
It's up there.
Okay.
I know. I'll check the Twitters.
The Twitters. I like it. Okay.
Melody's back.
Same hashtag.
CSTT. I think the more I have gotten comfortable in my computer science and programming knowledge, the more I see patterns across all of the problems I do. And I felt like I think that's true in other domains too. Oh my goodness, these are all oscillators in physics class. They're all oscillators. What? Okay, but in computer science, I'm like, oh, these are all the same pattern. Okay, and I think I'm really interested as an educator and an educational researcher to make those patterns accessible to our students. And thinking about naming those patterns, explicitly having them draw connections across those patterns can be productive. Okay, so here's one more pattern I show kids. This is a little small, but we start with code that draws this little ugly snowflake. Yeah, that's like the best description I've got. Okay, and so each time it goes out and then back in and then turns, and out and back in and turns. Okay, and so I have this piece where I go out and back in and then I turn. Okay, but instead of just going out and drawing a line and back in and turning, I could do something more interesting there. So even if I just draw a square, okay, I get a much cooler picture, okay? And I really like this one. Do you remember the dot one we looked at before? Okay, if I just take smaller steps in between those, instead of taking 30, if I take like 10, I get kind of like a little pie petal shape, yeah? Isn't that cute? And it's the same thing where I do something going out and I come back to where I was and then I turn some amount. And so I have students do each of these problems. And often when they see it, they approach it as a new problem. And they get to engage with these same ideas a second time as practice, and then we can connect across them.
Colleen?
Yeah?
What do you mean by have the students do the problem? What's the problem?
Oh, I give students this picture.
The picture, or is it the...
I give students this picture, and I have them write the code. Yeah.
But you say they have to do it with a loop or with a repeat, or do you let them, like some of them would do the easy way and just do line.
Oh yeah, this one is actually pretty cool because there are other interesting solutions of, you know, I start here and I go there and then to the middle. And this one actually in my class, I use it to talk about the fact that people have many different solutions. And we look as a class at many different solutions to this problem. And I also do a similar thing, but with just a cross, because that one is easier to wrap our heads around the solutions, but we can look at how there's many solutions. But in general, I give them the picture and ask them to draw it. So this one, it would be after they had drawn this and after they had drawn squares. Yeah. And this one, I think, is additionally cool because you can make it different colors by layering on the iteration pattern here, where each time through, I change the color by a certain amount. I set the color to red, and then I change the color, and it makes this beautiful little rainbow. Okay. All right, next, I'm going to tell you about 3 research projects that I've done centered around Scratch, okay? So this last piece was like gluttonous of like, this is why I think this is one of the things that brought me to teaching Scratch, and I think is so fun to get to teach with Scratch. Okay, so in this, most of my research has happened with kids, has happened in this summer camp for that's 36 hours. I teach 2 sections of it, and each section has between 20 and 24 kids. Okay, so my first summer doing this, I had one of the groups learn Scratch for 8 days, and one of the groups do the exact same problems, but in Logo. Excuse me. To have like a lot of overlap, we ended up with a lot of drawing. Okay, lots of shapes and lots of drawing. Okay, but they're doing the things in the same, they're doing the same tasks on the same day, and then answering isomorphic quiz questions each day. Okay? Yeah, students going into 6th grade and academically advanced students. Yeah. And so if you haven't seen Logo before, so Scratch is based on Logo, so the similarity is not a coincidence, but a lot of Scratch can be directly mapped to commands in Logo. So here's an example. Pen down is just pen down without a space. Repeat 4, forward 100, right turn 90 degrees. I don't know where my 90 degrees went. Let's pretend it had a 90 degrees right there. Okay, so there's a clear mapping, and so for every task I gave students and for every quiz question I gave students, there was a one-to-one mapping much like this. Okay? And here's what I found. Across these 2 groups, each that had 20, 25 students, these were both statistically significant that students who learned Scratch were more competent. They did better, particularly around loops and conditionals. but that my students who learned Logo were more confident in their programming ability. And that was statistically significant. Oh, the survey question, so self-report. So here are some hypotheses of why that's happening. And, you know, I look at this, I mean, okay, so with a small sample, I still got statistical significance. So there was a real gap between the Scratch students' confidence and the Logo students' confidence. The students who learned Logo were more confident. And I have a few hypotheses around why that was. One was, in Logo, the version I was using didn't have any kind of list of all of the commands that Logo might have, right? So as far as my students knew, they knew everything that Logo had to offer. They knew every piece of it. Okay, that's one possibility. And the students in Scratch, there were plenty of things in Scratch, you know, ghost effect. We didn't use ghost effect in my Scratch in those first 8 days of the class. So there could be things thinking about the extent to which seeing that menu gives them context of the world that's out there in Scratch and things that they don't know. Okay, that's hypothesis one. Hypothesis two is these kids don't know what programming is. Most of them, particularly in 2009 when I did this study, the kids didn't have prior experience. They had never seen this type of stuff before, but culturally they had ideas and expectations about computer science and about programming. And the next study we'll talk about is me trying to like get at some of those tacit assumptions about computer science. But one thing is just that Logo might have met their expectations about what programming looks like. Yeah.
And whether they saw code,
yeah.
It was exactly that.
I have students, because this year I'm not teaching Logo, but working with microworlds, like a lot of them, they have this idea, like because they're typing it in, and stuff, like that they embrace it on a different level. Like my kids love Scratch and they'll do that, but there's something, I just remember when I was teaching that, and like some kids, not all of them, but some would say, oh no, I like microworlds much better because, and that was the reason.
Yeah.
You know, these are like 6th graders, 7th graders, but it's the same idea, right? It's,
Same with the high school though.
It's in their head, right?
It's cultural.
Real program.
Turtle art. Do you know turtle art?
I don't know.
Okay. Turtle art is a very little program. That's the Turtle Graphics component, but it's blocks.
Oh, okay.
Now, see, I'm looking at this. So you're saying that one of your hypotheses is that since they didn't know there were 280 primitives in Logo, okay, so Turtle art has 50, less than 50.
Yeah.
It's just the turtle geometry component, but it's blocks. So unlike Scratch, where there's a zillion things, and some teachers I've worked with, they prefer turtle art as an intro because it's more limited, which is why a lot of kids don't like it. So I mean, this is, I think there's a teacher-kid difference here. But anyway, it's worth taking a look at, and it also has text Logo. You can switch to text to programming text.
Yeah.
So the mapping is even more direct than Scratch, from blocks to text.
Very cool. And you know, now after doing this study, what I do in that class is I teach Scratch, and when we spend a day where we do basically 6 days worth of activities that we did in Scratch in Logo. And all I do is I provide them a sheet that says, here was the block, here's what you type. And they're like, and some of the problems are still hard for them, right? Like some of the, you know, thinking about the iterations, some of those problems, even if they went back and did them in Scratch, would be hard for them. So it's good practice. But they get to, so now to try to make sure that my students get both perspectives and can make that connection to, you know, this physically typed languages, I have them do a bunch of those problems again in Logo. Yeah.
I'm just thinking it might also be interesting if you were looking at Scratch versus, say, Python or JavaScript, because of the complexity that's possible to create in Scratch more rapidly with blocks versus needing to learn more to do a similar, whereas here you're doing beat by beat by beat.
Right. I think, you know, I think when you start getting into the case where you're comparing them but you don't have isomorphic problems, the experimental design gets much more complex. But the thing that this research study, just a second, the thing that this research study really clued me into is I need better ways of understanding what kids expect when they walk in the door about learning computer science. What do they think is going to go on? And the extent to which I can build their efficacy within the domain is going to be limited by the extent to which they understand that what they are doing is computer science and is legitimate. Let me come here first. Yeah.
Well, I was just thinking when you were saying the split and going back and forth, there's a JavaScript games that are very simple games, but that you make with just like the mouse and stuff, and then you can see the JavaScript. And there's that website.
Yeah, so that
so
translation.
And the translation is, I think, what's so key, like what you were saying, being able to see the blocks, and then like the fact that Scratch has the text right on the blocks.
But it doesn't generate text code.
I know it doesn't generate text code.
Because RGBlocks, it's an Arduino program. It's blocks.
But it generates
the Arduino code, and it has to because it's actually just on top of it.
Right.
So, and if you change the blocks, you upload again, you get new Arduino code.
Yeah. Did you want to add something? Then we'll go back to Diana.
What the kids that you teach, are they in a sense self-selected? Like, are you teaching?
Totally.
Yeah. I'm just curious.
Yeah, totally self-selected. So it's kids participating in a summer enrichment program for academically talented students. And so there are other options at that grade level were like terrestrial trigonometry and creative writing corner, and you know, if they were going to participate in this summer enrichment program, and the program starts in first grade and goes through high school, and many of the kids go through it every summer.
And what community is this?
And this community is in the Bay Area. And most of the students pay $500 for the program, and then there's a limited number of students, typically 2 to 3 per class, that get scholarships. So it's not
so it's like Manhattan's private school kids.
I'm
thinking
like you just said Bay Area and 500 a week or 500.
500 for the 3 weeks.
Oh no, that's very cheap.
I also am not going to be able to provide any coherent mapping to anything in New York. I'm sorry. Yes. Yeah.
One of the fun projects that we grappled with this year is a K-12 curriculum for computer science. And one of the places that we started was language. We've now put it to rest for a while because we were grappling too much. But one of the questions that we raised was, does Scratch look enough like code? Because that's one thing that we, talked to the computer science department about, and there was really no definite answer, but what we really thought that Scratch does is it builds building blocks. When we start with our kindergartners and we're using a certain language and we're using certain words, and then we're doing the BBOTs and we're teaching patterns, patterns. And then, then we move up from BBOTs to Scratch Junior or, Lightbot. Lightbot is great for patterning and what you were doing before with like cycling out the fat, so to speak, and teaching that the needed pattern. And so I see this as just like a vehicle of like one to the other. And that's kind of like how we viewed both too, is and the kids love Scratch. And they do get confident about it, but my concern always has been is the whole gaming gratification thing, that there's too much gratification for like focus. Do you know what I mean? Like they're too focused on making the cookie dance and not focused on like the building components of what makes a cookie dance.
Yeah, and I wish I knew I was making good trade-offs in my teaching. So for example, in this 6th grade course, I've really focused on making it a challenging and enriching experience in terms of engaging with the computer science ideas. But for some students that might not be optimal, and I might be making it too hard, and they might be saying, well, yeah, I could do it, and Colleen talked a lot about how it was stretching my mind, but I might be turning some students off where I don't mean to. It's an open space, and I can't pretend I'm making anywhere close to the right decisions for my
I don't know
students.
if you've had the same observations, but I've had students who have gotten to a task and they like want A to do B, and they can't figure it out. And I've just kind of like sat back just to see what happens, and they'll abandon the task. They'll like move on to a new game. And so when I see them kind of like abandoning ship, I'll jump in and say, no, you can figure it out. You can figure it out. Like, just take your time and figure it out. And they're like, nah. And they just like move on. And like that gets really frustrating for me. So if you have any tips with that and like that kind of direction, that would be really helpful.
Yeah, and I think we can come up with those. I'm going to take one more, and then we're going to move on.
So like what you're talking about is like self-efficacy in the concepts, and like, sorry, I just want to comment, it's a really deep, hard thing to get at, and I think that is the right question, right? Like, yes, you want this thing, there's a way to get to it eventually. What are the strategies, what are the resources, how do you get the, like, I don't know what the answer is, but like that, I think that's one of the big important questions.
But it's what ties into, like, what's important to figure out, even as an adult. Like, okay, not that, it's sort of human nature.
But when I learn a new programming language, sometimes that's what happens, is I'm like headed in this direction. I'm like, I'm never going to be able to figure that out. And I might be right that I shouldn't continue down that path, and I'll learn some other corner of the language. So I don't know a priori that those U-turns that they make and redirections that they make are unproductive to them in the long term. I think it's a complex system. And I think if we can think about more tips in this space, that'll be helpful. So as we go through, I have 2 more projects that I'm going to talk about quickly before we're standing up again. But thinking about how to redirect kids productively in that direction. One tip I have is I don't let kids use the paint editor in Scratch in my class. I let them do it after class or whatever, that they can add their sprites and change their sprites, etc., but I don't let them do it in class. But when they get stuck on something, they open the paint editor, which is awesome because I can see their screen, and so I know it's like they are silently raising a red flag of I'm confused by opening their paint editor. And pretty consistently, these kids, when they get stuck on, they're supposed to solve this problem, will open the paint editor, and then I can intervene, right? And I don't treat it as a disciplinary thing. I treat it as like oh, cool, you're stuck. Yeah, basically, yeah. We also use little blue cards that they put on their monitor when they get stuck, so I know to come help them, but they can keep working and use both of their hands to keep working. And so it's just another blue flag for me. Okay. What do kids think counts as a programming language? I think this is a hard and interesting question to think about, particularly for these kids who have sort of cultural assumptions about it, but don't have explicit instruction around programming or words to talk about their expectations. So this was the research team that I did this with, and we have a publication from 2014 that I'm going to tell you about. So we showed kids, the same sixth grade population, after they'd done about an hour of Scratch, these pictures of programming environments. So this one is Eclipse, and we asked them, hey, is this not programming, somewhat like programming, or definitely programming? In general, students said it was definitely programming, and what I was interested in from a methodological perspective is like, how do we get at students' assumptions about these things? So I was really interested in what they said in justifying their answers. So they were saying, it looks like something that would be programming. Okay, that's not super helpful. It looks more official. Okay, we'll look through some more examples. Has anybody seen Code Spells? Yeah, it's Java, but in this like wizard frame. Okay. And so we asked them, is this not programming, somewhat like programming, definitely programming? And a student said, that looks like a game you could play online, and when you're playing a game, you're not programming, you're just playing a game. And this, I think, was instructive for me because I think a lot of times kids will describe their prior programming experience outside of Scratch as like playing a game. And a lot of times I think students experience working with Scratch is that it feels like a game. And so I think that's an interesting distinction that maybe not all of our students are going to make, but I think that this contributes to our understanding of some of the things kids might be thinking about. Okay, this one's my favorite. Do people recognize this picture from The Matrix? Okay, so here it was a little more spread. 11 students said definitely programming, 16 said somewhat, and 8 said not programming. And our students who said definitely programming said that's what the inside of a computer looks like, or it looks complicated. Okay, so, you know, I don't think that my students have seen, the 6th graders have seen the movie The Matrix. You know, so they maybe don't know like the cultural source of this. But I think there's more work to be done to be thinking about the extent to which our content interacts with students' tacit expectations of what they're going to be learning in a computer science class and what it means to do legitimate computer science. Now when I teach it, I like try and stand at the front and I'm like, I am the voice of authority. I have a PhD and I'm a computer science professor and this Scratch is computer science. But I still don't think I'm like very effective at convincing them of that. But I do all I can. Okay, an earlier study is 6th grade. So these are students going into 6th grade. Is their performance in a Scratch course correlated with their performance on standardized tests? So this is looking at my Scratch assessments in a class in 2011. And again, I want to remind you about the population that I'm serving here. So I was looking, when students are in the summer after 5th grade, their most recent California standardized test is their 4th grade standardized tests. Okay? So I'm looking at their 4th grade standardized tests. And over here is their mathematics scores and their English language arts scores. And then here's the important information, is in California, below 350 to 400 is proficient. So almost all of my students are advanced in both English language arts and mathematics in grade 4 standards. Okay? So dash your average? Sorry? Oh, dash is the median. Yeah. Okay, so this is my context, because I think that's, in all of the research I've been talking about, like an important thing to keep in mind of, you know, I think in my work I'm very careful about not overgeneralizing my claims of, I think, you know, the first one about logo versus Scratch and confidence versus competence, that convinces me that there's interesting and important questions there. Does it convince me that Scratch is better for teaching competence in computer science than Logo? No. Does it convince me that Scratch can't teach kids to be confident in programming? No. But it does convince me that there are interesting questions there, and this interplay between confidence and competence is interesting. Okay. But quick answer, yes. Students' 4th grade math performance is correlated with performance on Scratch quizzes in my class after the 5th grade, and it's significant at the 1% level, and their English language arts performance is not significantly, statistically significantly correlated. It is also positively correlated with their Scratch performance, but when you control for math performance, it's not statistically significant. And so there's a bunch of research over 30 years. Let me come back one slide. You know, before we had college programs training people to teach, to learn computer science, it was like we already needed computer scientists. And so people for a long time have been really interested in how do I pull a random person off the street and figure out if they're going to be good at learning computer science. And so a lot of research has gone into, well, can I look at their eye color? Can I look at their toenail size? Can I look at their... You name it, people have looked for correlations between a random person, properties about them, and how good are they at learning computer science, okay? Or how successful are they at learning computer science? A very reasonable approximation is over about 30, 35 years, we don't have strong predictors of, you know, what characteristics about someone makes them good at learning computer science. I have 2 points to make on that. One is because we don't have these correlations, people are like, It must just be a gene. Okay, right. I think there's no reason to believe that humans had evolved with a gene that was specific to a task and uncorrelated with other tasks, specific to a task that only recently existed. Okay? I don't know a lot of biology, but that doesn't sound super plausible to me. Okay? 2, it's just a narrative that helps perpetuate exclusion. Okay? So even if you think like, oh, there might be something to that, it's still exceptionally problematic. And 3, I think that there's stuff at these younger grades. I think there's an interesting overlap between computer science and these younger grade math expectations where there is an interconnection between the topics. Okay? And so that's something that I think is really interesting. So we've been talking about some of the movement. I want to look at a 4th grade math standard in California. Know the definition of right angle, an acute angle, and an obtuse angle. Understand that 90, 180, 270, and 360 are associated respectively with a quarter, half, 3/4, and full turns. If a kid comes into my class already knowing that, they're going to do better than a kid who comes into my class not already knowing that. I'm not saying necessarily that my class is going to teach them this. That'd be cool. But if a kid comes in with this content knowledge, they're going to be able to achieve on some of my geometry-based drawing activities. Okay? Here's another example. This is one of the released exams from that 4th grade math test. Square equals triangle plus 4. If triangle is 7, what is square? We haven't seen, sort of at the adult level, correlations between performance on other tests, other measures of individuals, and their performance learning computer science. But I think when we get to this level where we're like, how do you feel about variables? Does this feel okay? It makes sense that we're going to see more, that not having some of this reasoning skill might be more of a barrier to students in Scratch. Does that make sense?
This is 4th grade standard, this problem?
This is a released question from the 4th grade math test in California. Yeah, okay. So here's my claim, is that there's substantial overlap between the content of California's 2011 4th grade math standards and content in my Scratch course that does a lot with variables, with angles, reasoning about multiplication and addition, counting, doing multiplication accurately. Those are all skills that I build on in my class. Okay. We're going to take another break, and we're going to stand up. Our first one is, raise your hand if you've never taught Scratch. Woot, 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 woot. We're just going to spread you out. Yeah? And you're going to be our facilitators. Does that feel okay? Yeah? Okay. When you introduce new blocks, do you do so first by the block by itself, or having the student look at a block within a larger context? So like, a framing problem. Does this question make sense? Okay, stand up and start talking. What you're talking about is discuss in your group a specific example. A specific example of where you introduce the block in isolation versus where you introduce the block within a larger context or larger project. So I think hearing examples of what's a block that you think, oh, let me introduce this in isolation before I motivate it. Or let me motivate it abstractly.
What does this bring up?
But I think we don't say like, here's the move in the pen block, like let's just see what happens, and then it's always like some small context. Whether it's right or wrong, it is like context. We want to do this. And here's just like
I'm thinking about Booleans. You can teach just Boolean operators and as single concepts. But it's in the we always teach it in the context of the conditional additional gate booleans, and then we drill down and do a lot of different examples.
I mean, I'm facilitating.
No, we don't usually, you can say like this evaluation shows us click on it. Usually that's like.
The question here is about introduction blocks.
So one of the things I do is I have a self-paced curriculum that resets every 3 hours. And so if the students has a lot of experience, they go through the required tasks in that curriculum quickly. And then there's something I call a super cool at the end, which is reinforcing and practice of those same concepts, but doing something more creative. So my first day is making a song. You know, a later day is making a play. And so, yeah, you know, they might include random blocks and other things in it, but they still go through the same curriculum.
Is that part of the videos that you make?
Yeah, it's the edX course is set up that way. It's structured as 6 weeks, and each one has 2 parts. And at the end of each part, there's I call it a super cool, which has that extended practice.
Okay.
I just feel like it should be up to them to discover.
I'm going to count you down 10, 2, 1. Okay, let's hear from this group. We're going to hear from this group. What's a specific block that you introduce in isolation?
The hell block.
The what?
We're going to say change costume. Like the visual blocks that are very easy to see.
To do it, awesome. So it's easily motivated.
Easily seen. Like it's very concrete. It's easily concrete.
Cool.
Change pen color. Those are the ones that are
In isolation.
In isolation.
Okay, cool. Setter group, do you want to share out one?
So our group wrestled with the question. We realized we do both. We talked a lot about the curriculum that Ron and I teach, where we always lead with the context of the computer science landscape. You know, like what interactions are seen in this example, or font size changes. What's really going on behind that, and then we have that concept that then we're talking about, which will involve some different blocks, and then leading them into an application program that's missing pieces that target that concept. So there's some time in there where we're talking about a specific block of isolation, but it was never the introduction. But it is definitely part of the instruction.
Sorry.
Leading back into context.
Yeah, I love it. You could spend all day writing tips about specific examples of that. You know what I mean? Which would be cool. Okay, other share out from this group?
Well, there's a kind of a difference of opinion.
Uh-huh.
We had some folks who believe very strongly that you need to start with building blocks. You start with block instruction first before you can get to the context. And then we had others who thought you needed to have the context in order to give the blocks relevancy. And there's kind of an agreement that both points of view are valid, and they may actually exist among a continuum, but they actually might have specific applicability based upon the student's skill level and the problem at hand.
Awesome. Yeah.
So as an example, using broadcasts versus weights.
Love it.
We also talked about play note being a little composite function in and of itself, even though it's a single block, because it takes 2 different types of arguments, and you can learn about how that works just on the single block level and then expand.
And another thing is talking about when do you explicitly teach something versus show one student and allow that student to spread the idea.
Just in time versus the whole group.
Awesome. Can we hear from this group?
Well, we actually talked similar about using, like the idea, like if I have students create a dialogue at the very beginning, and then talk about like what was easy about, like how it worked and how it didn't work. So I'm kind of big on having them come up with the problems that happen and then go, oh, guess what, there's another way we could do this.
Mhm.
Say, like using the broadcast, because that way, if they've gone through the process of experiencing it and understanding what the limitations were using weight, then they can fully or better understand why you want to use broadcast instead of just throwing it at them and saying, this is a good way to do it. It's like,
Mhm.
but they didn't have a reason for it. I like giving them, having them come, figure out why they do it.
Yeah, like creating a challenge rather than saying this is a block, this is what it does, saying the challenge for today is 2,
Mhm.
and then finding which blocks, because also in Scratch it's not always one block.
Yeah.
So a good example is moving with keyboard keys.
Mhm.
There are 2 very distinct ways to do that, and they each have advantages and disadvantages.
Love it. Okay. We're going to do one more of these, and then we're going to have people pull tips, pull Post-its that they want to write into tips. So this is, do your students find Scratch difficult? We're going to go on the left, not really, and on the right, yes. And the key piece to separate is really, do you want to discuss, what have students been able to do in Scratch that's really amazed and surprised you? Concrete examples of that will be really helpful. And what specific things do students struggle with? Okay. So not really, they find it difficult. I'm so impressed. I want to talk about things that they do that's impressive, or there are specific things that they do that's where they get stuck. And then our facilitators are going to help us going. Okay, go.
And actually, usually Scratch adding things to that bar chart during the day.
Like I was trying to think, like what's the most amazing probably similar in that there's a pattern. You can build patterns.
9, 8, 1. I have made 9 Google Forms. Raise your hand if you've used a Google form before. Yeah. So what you're going to do is you're going to go. We've got this link, tinyurl.com, CSTT, CSNYC. What I'm going to have you do is go to the back of the room in just a second, and I want you to grab one Post-it, and that Post-it should be one where you say, I can provide a super concrete thing that would, like something, a tiny nugget that I could hand to a teacher, that a teacher would read without any context around it. I could provide something super concrete. So here is for one block, one way I introduce it. Like super, super, super narrow. Yeah? Not like, it's good to motivate your students. It's good to allow them to be, something actionable. And then I hope that each of these has sort of appropriate questions that you might want to address. So why did you want to get started teaching Scratch? So how long have you taught Scratch? Why did you want to get started? How did you sell the importance of Scratch? And then your name and email and any collaborators. So you can work on these with a partner, etc. Yeah? If any of the links aren't working, let me know. So for now, folks, in between the whiteboards, there's another category, which is questions that have come up. And if you can provide even one answer to that question, grab the Post-it note and start working on it. Okay? So if people can head towards the back and start grabbing Post-it notes, and then head back to your table. Yeah.
Oh yeah, I have to. Like it didn't impact me. I'm going to Google contacts. Unless if I'm doing something like this, I can't stand up. But I'm still used to the make sense one.
That's very cute. Completely finished, but
That's
so great.
And if you can leave the Post-it notes, some of the general topics where there were specific examples I'll tweet those out and try and get people to contribute more specific examples.
So we shouldn't be taking.
Oh, you should take them to your table, but then if you just put them somewhere, I'll take them home. Okay. So I think from here, we're just going to keep chit-chatting, entering tips, having a lovely time. Let's do one more round of applause for Cornell Tech and CSNYC for hosting.
And for Colleen Tech.
Oh, thanks, Dad. Thanks. Okay, so let's keep hanging out. Cool, bye. Okay.